Hi guys, in this video we'll discuss about two-phase nanofluid simulation, how to simulate in the Ansys Fluent. So prior to going into that simulation, we'll just discuss about some theory about the conservation equations and the source terms which are very significant to simulate the two-phase approach. So here on the screen you can see the nanoparticles agglomerated and the nanoparticles that are suspended freely. So now the contents in this tutorial or in this video is first part is introduction, second one is conservation equations that are involved, third one is discussion on significance of terms, pre-processing and setup is the fourth one, post-processing and the discussion of the results is the last one. So now as an introduction, a nanofluid is a fluid containing nanometer sized particles called as nanoparticles. You can see in the below screen this is a base fluid, maybe you can take it as a water, so in which the nanoparticles which are less than 10 power minus 9 meter size are present, and these have a different direction. They will not have a constant direction. These are the nanoparticles, so these have a different direction along which they flow inside a fluid. So these fluids are engineered colloidal suspensions of nanoparticles in the base fluid. So this entire fluid along with nanoparticles is called as nanofluid, which has the suspensions of nanoparticles. So these nanoparticles can be a combination of metals, oxides, or carbides, or carbon nanotubes also. But in our simulation, we are considering aluminum oxide nanoparticles or aluminum oxide nanofluid. So I have just zoomed in the picture where these are the different nanoparticles have different directions of motion when compared to the base fluid, which flows only in single particular direction or predominantly in single particular direction, but whereas the particles has very differential or discrete motion, and the heat flux is applied on this surface. What is the significance of volume fraction of the nanoparticles in the base fluid, how it increases the heat transfer coefficient, all those will be discussed in this video. So these are the set of conservation equations which would be solved in the two-phase approach using the Eulerian model in the Ansys Fluent. So the first one is the continuity equation, where you can see alpha is the volume fraction, rho is the density of any particular phase, and these are also a velocity term that is been involved, and m dot pq or m dot qp is nothing but the mass that is being transferred from phase 1 or phase p to phase q or phase q to phase p. So this is the mass transfer that occurs from one phase to other, and SQ is the source term. So for our simulation, there is no transfer of fluid from fluid to solid or from solid to fluid. So you can take m dot pq is 0 and m dot qp is also 0. So we can neglect those two things, and there is no extra source term also. So SQ is also 0. So now if you, so as you can see here in the momentum equation, the liquid phase, so this is the acceleration term which varies with respect to time. This is the acceleration term which varies with respect to space, and this is the pressure gradient that is acting in the fluid. As we mentioned, alpha is the fluid fraction, and tau q is the stress strain tensor, and this alpha q rho q g is due to the body force, self weight, and rpq is the momentum transfer. And as I've stated earlier, m dot pq and m dot qp both are zeros, and fq is the extra amount of force that acts on the body, f lift is the lift force that is acting, and fvmq is the virtual mass force that acts on the body or the fluid. rpq, so as I've stated about, this is the momentum transfer that occurs due to this transfer coefficient or the momentum exchange between solid and liquid. So this is the transfer coefficient kpq. Vp minus vq is the change in velocity between the two phases. When you come to solid phase, there's an extra term, delta ps. So the delta ps is nothing but the term which signifies the solids pressurized due to maybe kinetic energy, or it can be due to extra term like a interaction or coefficient of restitution, like two coming and colliding. So that term is extra amount of stress that is created, or that is extra amount of pressure. Actual sense is that is the extra amount of pressure that is being created due to these interactions. So that would also plays a significant role in the solid phase conservation principle. And this delta Ts is a solid stress rate tensor. As we have a tau q, it is a tau s, and this is a solid body force. Similarly, this KL is the coefficient. Here we have a KPQ, right? So KPQ and KLS, nothing but same. It is like KPQ is equals to minus KQP is equals to KLS. So minus KQP is equals to KLS. So both would be same in magnitude but minus in sign. That's it. Momentum exchange, one is for positive and other phase it would be negative. Similarly, m dot ls and m dot sl, there is no mass transfer, these two terms would be zero. And lift force that is been acted, and this is the virtual mass force. And this is the extra source term. If there is any other extra source, that would be considered. So, or else you can take it as zero. And this is the energy equation that would be solved with respect to enthalpies, specific enthalpies in particular. And this alpha q is nothing but the volume fraction of the solid or liquid phases, and this is a variation of pressure with respect to time, and this is a terms which signifies the change in energy states or that causes due to these collisions. And importantly, QPQ is the heat transfer that occurs between two phases, how the heat transfer rate exchange between the two phases. So this may plays a major role in having the interaction between solid to liquid in heat transfer, or in basically nanofluid that is passing through a heated pipe. Similarly, K, as mentioned, m dot pq and m dot qp would be zeros. So now individually we need to find out kpq, or which is same as kls minus kls, and we need to know the significance or the tau is how we will find. We need to know how we need to find delta ps. We need to know how we need to find this f lift, f virtual mass force, and we need to find here qpq. So all those terms has a significant in or has a major role in two-phase nanofluid simulation. So we'll let us see that one by one. So this is a virtual mass force. So virtual mass force comes into act if there is a very relative acceleration with respect to two phases. There's a huge acceleration with respect to two phases. This comes into role, or we can take it as zero. There is no huge acceleration. So this is a lift force that comes into act when the particles are dense in nature and when it's leaving. So this comes into act, and this is the fluid solid exchange coefficient, where the momentum exchange between two fluid as well as solid. So it depends on volume fraction, it depends on density, it depends on f. That f is nothing but a term which depends on the coefficient of drag. So it is a term which depends on the coefficient of drag, and it depends on RES. So RES is called as relative Reynolds number. So it is a relative Reynolds number. It's like a difference between Reynolds number of fluid with respect to solid. In that way you can think. And VRS is the relative solid particles velocity. So this is the F term that need to be incorporated here. Don't worry, you need not keep all those things, but I am explaining the significance of each term that we are selecting in the simulation. And tau is the shear stress that is been defined in this way. The solids pressure, what I have mentioned in the previous slide. So this is a solids pressure, PS. So it mainly depends on this phi, or you can talk it as theta. So theta S. This theta S is nothing but granular temperature. So granular temperature. So this granular temperature, you don't have a misconception that it is a temperature. It is not a temperature. It is a kinetic energy that is being possessed by the body. So we need to separately solve an equation in order to find this theta S. So it is not that easy to get this theta S, because it is a quantum mechanics like thing where we need to solve in particular this theta S. How the particles kinetic energy is getting varied with respect to this fluid, or in colliding with the neighboring solid particles, and all those things. ESS is a coefficient of restitution. I think everybody know about coefficient of restitution. Here by default we will take it as 0.9. And the next one is G naught SS. G naught SS or G naught is a radial distribution. So radial distribution means what is the probability that a particle would hit another particle. So you can see here these are the particles. Would really this particle hit this or not? If this particle doesn't hit this, then there would be no solid pressure, then there will be no solid stress. So there would be so many terms that can be zero. So we need to know whether the solid has a probability of hitting the particle or not. So that would be taken care by this G naught. And this S is the mean distance between the particles and dP is the diameter of the particle. So now if you consider here, if S is 0, then the radial distribution become infinity. So interparticle distance is 0, then there is no probability of collision because it was touching and going. So there is no probability of collision. So if S naught tends to infinity, this becomes 1. So there is every probability that it can hit the other particles. So this distribution is very important in order to judge whether it hits the other particles, and if it hits, what is the pressure that is been extra created, what are the stresses that are been extra created, any variation in the momentum exchange between the solids and liquids, all those comes into role. So this radial distribution helps in having the probability of hitting the other particles. So that is called as granular temperature. I have already said. So that is theta s. For that theta s, we need to solve this set of conservation equation, which is an extra burden to our regular solving capacity. So regularly we will solve one momentum equation, one continuity equation, one energy equation. But now here we need to solve two momentum, two continuity, and two energy. Apart from this, now this is the extra granular temperature equation also we need to solve in order to know the temperatures, or sorry, granular temperature that helps in finding out the pressure that is been exerted. So all those extra amount of equations we need to solve in two-phase nanofluid. So this makes the simulation very computationally expensive. So these are the significance of each terms, how the collisional dissipation of energy takes place, how the energy exchange between solids and liquid take place. So all this has its individual significance. So if you want more in detail, you can go through Fluent manual, which is available in the internet. And the next one is a heat exchange coefficient. As I mentioned, how the heat being exchanged between solid and liquid. So that is HPQ, as I mentioned here, maybe here, yeah, that is a QPQ, where the heat exchange between solid and liquid, and H is the heat transfer coefficient, TP minus TQ is the temperature difference between two phases, and HPQ depends on the Nusselt number of the particles as well as the conductivity of the phases. So now HPQ, if it is solid it is HPQ, and if it is liquid it is minus HQP. So both would be same, but sign difference that we need to incorporate in the conservation equations. So all these equations need to be solved in order to have a set of two-phase approach. So now this is the solid state stress tensor which we have left finally. So in the solid state stress tensor, I think we have a good knowledge on stress strain tensor for liquid phases. But this is the extra term which been introduced you in this solid phase, that is the extra stress that is been created due to the viscosities like collisional viscosity or kinetic viscosity and frictional viscosity. So collision viscosity is like when two solids get collided with particles, or when two solids get collided. So that is the extra amount of viscosity that need to be incorporated. And if it has a self vibration or kinetic energy, so that has one type of shear stress or shear rate. So all these need to be involved, combined in order to get mu s. So the last but not the least, that is frictional viscosity. So frictional viscosity would come into role when the particles are agglomerated, or particles has less space to move, or they are concentrated in a particular area. If that concentration has increased a limit, by default we will take it as 0.63. So it can be more than 0.63, it all depends on our experimental based values, but there by default Fluent has taken it as 0.63. If it is more than 0.63, then there is every probability that the two particles start rubbing each other. So that is the frictional part which we need to consider. Now the fluid would be turned into a viscous plastic transition region. So in that cases, if it is more than 0.63, automatically it will involve this frictional coefficient also into the this solid stress tensor calculations. So this is the extra part which need to be involved when the fractional or packaging limit is less than, or sorry, is more than 0.63. So this is a brief description about the two-phase equations that would be involved in this solving approach. So now we will get to the pre-processing and the setup conditions, and it would be much more clear to you guys. So this is a simple geometry what I have considered. It's a 2D model, that's it. So I can just check, let you know what are the dimensions. So this is 7 mm and this is 100 mm, that's it, nothing more than that. When I went to mesh, what are the strategy I have considered is, so this is the mesh. So the mesh count should be less than 50,000. So you can see, as these are the walls, I'm given an edge sizing. So these are the two edges what I have selected. This is one edge, this is one edge. Edge sizing, you can select this edge symbol, go to this, select this, right click, insert sizing. After that, you will get this edge sizing. So this is the edge sizing, first edge sizing, and I have given number of divisions as 60, and this has my bias type and bias factor is 5. So these you can get. And the next one is edge sizing 2. This is the other edge sizing. Here there is no bias. I have given 800 divisions. Next I have given the face mesh to this. So all the quadrilaterals would be created. So these are the 3 steps which I have done. And in the named sections, this is the inlet, this is the wall flux on which the heat is given, and this is the outlet. Right, so when we will go into Fluent, so this is the general setup what I have given. So this here I will consider the steady phase approach. Steady phase approach is only practical or correct when the granular temperature is low. So as I was previously discussed, if the molecules are moving at a high kinetic energy, then there is no steady state at all, because it is a transient. It depends on time. If they move very vibrantly, so if there is no vibrations at that extent, it is very low, then yes, you can assume the steady state motion, or else it is not practical to apply the steady state. So here I have applied steady state because I have to granular temperature as very low value. Then I went into multi-phase. I have activated Eulerian implicit scheme, number of Eulerian phases as 2, and I have clicked OK. Yeah, double precision need to run. Yeah, it's no problem. It's just a warning. You can start with the double precision itself. And after that, I went into materials. I've added fluid. In that, I've selected fluid database. In fluid itself, I've selected one material as my water liquid. I've created copy, and other material is aluminum solid what I have selected, and I have created copy close. And after that I have left water liquid as it is, but I have changed the aluminum properties. So I have considered here aluminum oxide. It is not solid, you can consider as aluminum oxide nano particles. So the density is 3970, specific heat is 765, thermal conductivity is 40. Viscosity doesn't play any role, because even though it is given, it has no role to play. If you give constant 0 also, it doesn't have any difference. Molecular weight is 101.96 for aluminum oxide. Change, create, overwrite, yes, because I've changed the name. Okay, aluminum already exists, so I will give this as aluminum ALO. Change, create, yes. Click on close. So now you got aluminum oxide. Open this, you check, right? After that, I have again went into the phases. So I'll get 2 phases. Primary phase I have selected as water liquid. Secondary phase I have selected as aluminum oxide. In aluminum oxide, I have clicked granular. If you want solid to be activated, you need to click on granular. After clicking on the granular, you go into partial differentiation, and in the diameter, I have considered 1 e power minus 5 as my dia. So you can vary. So if you go for nanoparticles, you can go for up to 9. So or else I'll keep here 9, 1 e power minus 9 as my particle diameter. If it's 10 nano, okay, then I'll consider 10 nanometers. So it is 10 e power 1 e power minus 8, 10 nanometers. And the granular viscosity is model what I've selected is symbol and O'Brien. Bulk viscosity acts if there is an opposition of the solid particles due to the compressibility effect of liquid. As water is incompressible, it doesn't have any effect. So I can select constant and the value is 0 because the particles will not have a significant effect due to this compressibility effect of liquids. So that I can consider 0. If it is compressible like gases, then you cannot go for 0. And the frictional viscosity, as I have said, comes into role when the particles accumulate within a region. Like when these particles are in this vicinity, if there are very more in number, then you need to consider that. I have given only volume fraction 0.02, so there would be not that much frictional effects. So I have considered frictional viscosity as none. Nonal conductivity I have considered symbol and O'Brien. Solids pressure also I have considered symbol and O'Brien. These are the two methods proposed by the scientists. And the radial distribution I have selected Lunetal. Elastic modulus automatically selected derived option, and packing limit what I have mentioned, packing fraction. So for the frictional viscosity term, actually the packing limit, if it is more than 0.63, then you need to go for frictional viscosity activated. So these are by default value. I've left it. I've clicked on 0. So I've clicked on OK. Next, interactions. Now interaction between the two phases. By default, the virtual mass coefficient is 0.5. I have left it, but actually, if you just want to model it, I've already shown it to you. The virtual mass coefficient. This is a virtual mass coefficient that the extra force that will act in the role. So you can interpret and keep the values, or you can go for any user-defined function also how it varies. But default, I have kept it 0. And the drag force, yeah, symbol and O'Brien have used. Lift, because the particles are very small in size, nanoparticles, so there is would be no lift force that would be occur on the solid due to the fluid, right? So lift force acts due to the fluid on the solid due to the pressure difference or velocity difference. So that I have neglected because the size is low. Collisions, yeah, restitution, coefficient of restitution I have given 0.9. So the coefficient of restitution is 0.9. What we have considered is from here. This is the coefficient of restitution, ESS. Heat transfer is two-way resistance I have considered. In that I have used from liquid to solid, from solid to liquid. So both I have used gun models. And there is no mass transfer because it is not a volatile substance or evaporating substance. So there is no mass transfer, 0. And the surface tension, nothing, no surface tension I have activated. Interfacial area is that the interface mass, momentum and energy transfers which across interface takes place. I used higher particle approach. Okay. Close. Now I have used activated energy as on and viscosity as laminar approach. And in the cell zone conditions, in the fluid, so it would be a mixture, both combination of solid plus liquid. So in the boundary conditions, in the inlet, I have given a velocity inlet. Phase 1 velocity or the water velocity is 0.01 meter per second, and this has a Reynolds number less than 2000 because it's a laminar flow. Consider less than 2000. Temperature at which it is entering is 300. Reynolds number I have calculated using rho v d by mu. So d is a 7 mm. What I have mentioned, hydraulic diameter, I have calculated. I got less than 2000. So click on OK. Next, go to phase 2. So here the point, granular temperatures. I have given a very low value of 0.01. So steady state is possible. If the value is high, it cannot come to a steady state. That I will show in the video itself. Wait. And the temperature is 300 Kelvin at which the particles or the aluminum oxide particles are entering, because phase 2 is aluminum oxide. And the multi-phase fraction, maybe I'll take it as 0.02. So volume fraction is 0.02. So it is so common in the literature that as the volume fraction increases, heat transfer coefficient need to increase. That also will prove here. So yeah, this is the phase interactions, and in the phases, just checking the aluminum oxide. whether I've given the correct or not. And outlet, yeah, this is a pressure outlet. So for both, the pressure outlet is the atmosphere, 0 gauge pressure. As it is open atmosphere, reference pressure is atmospheric pressure, so gauge pressure should be 0 when it is released to atmosphere. And in the wall flex, I have given a value of heat flux 10,000 watt per meter square. So click on OK. In the methods, I have given coupled, pseudo transient, and in the controls, so these are the controls what I have given. You can just have these controls on your board also. And the report definitions, I just monitored one plot which is nothing but the outlet temperature. So I need to have more monitor in order to confirm my convergence. So that monitor is nothing but area weighted average of the temperature phase 1 at the outlet. I've clicked on OK. So if that has no variation with respect to iterations, then I can say that the solution is converged. Right? So I went into initialization. I'll initialize. So I'll click on run calculate. So the run is completed. You can see the residuals are stable and converged. The monitor point also converged to what we have considered. So we'll just check the heat transfer coefficient value. I have changed the reference value hydraulic diameter to 0.07007 because it is 7 mm the diameter. And the temperature is 288.16. I took the reference temperature. So go to surface integral, wall fluxes, heat transfer coefficient for this region compute. So it is 403 around. So now we just check the counters also. Display. Yeah, so this is the volume fraction of phase 2. You can see red color at the walls because there is no velocity when it's near the walls. So if there is no velocity, the particles will be trapped there and they cannot move. So there is much agglomeration near the walls compared to the center region. That's the reason why there is more agglomeration here compared to the center region. And we'll just check the temperature also. For the temperature is for phase 1. Yeah, temperature also because it is not yet fully developed. It takes some time to develop. So here the velocity will be very high. So and the temperature also will not come easily attained. And you can see this is the thermal boundary layer that is been gradually developing. You can see. So this is the thermal boundary layer that has been formed. And what else you can take? Maybe you can check down. So you can check this is the hydrodynamic boundary layer that is being formed, and it is just taking some time to get fully developed. After some time, it is been completely developed, and the profile is a parabolic profile. So if you want to have a parabolic profile checking also, you can check here. Just go to plots, XY plot, and plot direction is along Y. So keep this 0, this is 1, and the value of velocity and to phase 1 direction vector is on the outlet. So you can see this parabolic profile on the outlet, but whereas inlet it will not have a parabolic profile, it has a straight line. So that is a straight line. So it is so clear that at the outlet it is getting fully developed. So now we will go for 0.04 volume fraction and see what exactly the results would be. What happens to the volume fraction? Your temperature profiles and heat transfer coefficient. Does it increase or no? according to journal publications it need to increase. We'll just verify now. For 0.04 volume fraction, you can see here in the multi-phase. So these are the results. So now it has been stabilized and the value is constant here. So now if you go to reports and check the surface integrals, derivative average, heat flux, and surface heat transfer coefficient for wall flux, the value is 460.3363. So it is more than the 0.02 volume fraction. So I think it is clear now. So in this case we will check when you try to increase the granular temperature, what happens? Can it be steady state or not? Whether we'll get this stability result, whether we have this type of residuals or not. Just increase the value to 50. Now again I initialize. Within 20 to 30 iterations you will come to know, because it starts oscillating hugely. It means it cannot be steady. You can check here. So you can see here it is just oscillating. It was not going up, not converging. So I stopped after 100 iterations. So if the granular temperature is very high, I mean the kinetic energy with which the molecules are vibrating is very high, it is better you need to go for transient simulation instead of steady simulation. I think we'll just check down wall heat flux, because yeah, so it is obviously high because as the granular temperature is high, more vibrations, so more amount of heat can be dissipated. So with more granular temperature, pressure drop will be huge. So I think guys, this had made some sense to you. Maybe I'll just show you the contours also. So this is a temperature which is not getting settled down because I have stopped in between, but it is not perfect to have it a steady condition for high granular.